Coś mrugnęło, ale dalej działa. Dobrze. Dobrze.
It is my great pleasure to introduce Tomasz Downarowicz. He is a professor at the Department of Mathematics, Wrocław University of Science and Technology. More precisely, he is Professor Magnus, which is the highest position, distinction at the university. He is also the director of the Ryl-Nardzewski Center, which is some new thing to promote science in honor of well-known, I guess you all know the name of Ryl-Nardzewski. He's also vice president of Polish Mathematical Society. We were born the same year and we became students the same year, the same department, but he in mathematics and me in physics. And then we haven't seen for a long time, and then our trajectories cross, which is maybe the example of the ergodic theory, in a sense.
Recurrence theorem.
Huh?
Recurrence theorem.
Yes. So that's exactly the domain and specialty of Tomasz Downarowicz, which is the dynamical systems in general, ergodic theory more precisely, and the entropy aspect of the ergodic theory. Well, he has, of course, many papers, but visiting many places, and wrote a monography, Cambridge University Press. This is exactly entropy in dynamical systems. And for his work, he was granted the main prize of the Polish Mathematical Society in honor, in memory of Stefan Banach. I think we can offer him a tablet and screen, yes, and the floor.
Thank you very much for this wonderful introduction. It's a rare pleasure to be introduced in this way, so thank you very much. And let me start by making a comment about the title. As you see, I have introduced some changes. I did not change the title so that the old version is not visible. It is still visible because this title was announced in the program, so I didn't want to destroy completely the program. But when I started preparing this talk, I realized that I wanted to say too much in too short time. And for those of you who are not familiar with the topic, this would be a killer. So I shifted the topic from the more advanced matters to more elementary matters. And the blue things are added at the beginning. So these are introductory things to dynamical systems. Okay, let me start. Let's see if it works. This is forward, I guess. Yes. Okay, so in the theory of dynamical systems, we consider many types of dynamical systems, and today I will talk about just one of them, which is topological dynamical systems. And the most classical version consists of a compact metric space, that is this X, and a continuous transformation of X. So it's a function from X to X. And sometimes we consider homeomorphisms, and then we can iterate this transformation forward and backward. So in case of a continuous action, we can only consider iterations forward, so we have an action of the natural numbers. I will explain that in a moment. And for homeomorphism, we have an action of the group of integers. Okay. So what is the subject of interest for dynamicists who study these dynamical systems is the behavior of orbits. So we look at single point and we trace its future or past if we have the past, if the transformation is invertible. Otherwise, we go forward and it traces the orbit. So the orbit is the most important object. It's just the images of x under consecutive iterates of our transformation. And what we want to know about such a system, there are really many aspects that are of interest. I will only mention one today. So, suppose that we observe this system with some limited resolution. So, for example, we observe it on a screen of a computer, and if two dots are closer than the size of a pixel, we will not be able to distinguish these 2 points. They will show on the screen as the same dot. So we have some limited resolution. And also we have limited time for conducting our observations. The time, in this case, because we have discrete time, the time are integers. So we observe the system from 0 to, say, n-1, not to n, just because we want the length of the interval to be equal to n. So, 2 points in the system are called indistinguishable with respect to our epsilon and n, to our parameters, if throughout all this time we don't see the difference between them. So they are closer than epsilon throughout this time. And d here is the metric in our space. Here is the illustration of this phenomenon. We start with 2 points x prime and x, and their orbits remain close throughout this time period n steps, and they are so close that with our device we cannot distinguish. They are closer than epsilon. Okay, so what we are interested in is so-called complexity of the system. So how complicated is the system, and how to measure this complication, this complexity. Namely, we want to know how many, maximally, how many orbits can we see as separate objects. So this set E here, it's not necessarily unique. There may be many such sets, so we choose one with maximal cardinality. We choose the maximal number of orbits such that all of them pairwise can be distinguished, that at some point of the time they will be farther away than epsilon. So then we call them n epsilon distinguishable. They do not satisfy the indistinguishability condition. And this notion of complexity already gives us some classification of systems. Namely, the complexity will usually grow in time, because if we can distinguish 2 points in time period from 0 to n-1, and we observe the system even longer, then of course we won't lose the distinguishability between these points, because they have already been distinguished. So the number of distinguishable orbits can only grow. We have some increasing function of time, and the question is how quickly this function increases. So there may be linear growth, there may be polynomial growth, there may be sub-exponential intermediate, higher than polynomial, lower than exponential. And finally, there may be exponential growth. So for today's lecture, we will only distinguish these 2 cases, sub-exponential and exponential. We are not concerned about polynomial, linear, and so on, although these are objects of very extensive studies, and I'm just sketching the most most studied criteria here. So we have sub-exponential growth of complexity if for any parameter alpha, here this complexity becomes smaller than 2 to n alpha with time. And exponential if the growth is like 2 to n alpha. You can imagine that 2 to alpha is some beta, which is bigger than 1. And then you have beta to n. So it doesn't matter how you look at it, but it's more convenient to put this free parameter alpha to the exponent. But you can think of this as being part of the base as well. Okay, so how to compute this alpha from the complexity growth? Well, you just take how to distract alpha from 2 to n alpha. You have to take logarithm and divide by n, right? So you take logarithm of the complexity, logarithm base 2, and divide. By the way, this base sometimes is e, is natural log, sometimes is decimal. It's completely arbitrary which one you choose. Binary is good because it refers to the notion of a bit of information. 1 bit of information is a 0-1 type question. So log of 2 refers to binary type of information. Okay, so, and we take lim sub because a priori we don't know whether the limit exists or not, so we take the maximal limit. Okay, and it's called the rate of exponential growth of the epsilon complexity or epsilon entropy.
Sorry, just a quick question. Alpha should be greater than 1 or 0 in the second bullet for exponential?
Maybe alpha should be bigger than 0, of course. Yeah.
0.
Initially I wrote
2
alpha to power n.
Okay.
And then I switched and forgot to fix this. Thank you. I will fix this for future use, maybe. Okay, so this is a little too complicated for us because the system in a general compact space, there may be very tiny distances between points and things by continuity, there are already some limitations. For example, if you take the interval and you want to apply some continuous mapping, then you cannot do everything. If you take a 0-dimensional space, you have much more freedom because you can break the space into pieces, permute them. For example, interval exchange transformations are discontinuous. So if we limit ourselves to just continuous transformation, many important phenomena fall out by lack of continuity. So if you want an interval, you want to cut it at some place and exchange these two pieces, right? You're already discontinuous. Of course, you can do it by wrapping this interval around and rotating. That does the job, but I will not talk about this. So we will now work with 0-dimensional spaces, which are much nicer. So we take some finite set called alphabet. Very often it's just 0 and 1. We have then the binary system. And we look at the space lambda to power n or lambda to power z. Lambda to power n are one-sided sequences of, say, zeros and ones, and lambda to power z are bilateral sequences of zeros and ones or some more digits, maybe from 0 to 9. Then we are in decimal system. And then what can we do with these sequences? We can shift them. So here is the formula. The formula is not very nice because it assumes that everybody understands what this double parenthesis with subscript n means. So very precisely writing this down, x has to be explained. It's a sequence x sub n where n belongs to n. It should be n here. I have this marker. No, how was I? Okay, this guy. So I have this here, and this should be n here. Sorry about the typo. Okay, so then the image of this x is some y, where y has its own coordinates, y sub n, and the rule is that y sub n equals x sub n plus 1. And if you work with lambda to the power z, it's the same story, except that the sequence is two-sided. There is a big difference, though, because if we take lambda to power n, then by shifting, we lose information because the first digit disappears. If we have lambda to power z, then the shift is an invertible transformation because we don't lose any information. We just shift the sequence, but we can shift it back and completely reconstruct the original. Here, in this example, the first 0 is lost. So for lambda to power z, we only have a continuous but not invertible transformation. If the alphabet is 0, 1, it's 2 to 1. If the alphabet was 0 to 9, it would be 10 to 1. Okay, so now the most important object for dynamist is so-called subshift or symbolic system, aka, everybody knows, also known as. What is it? It's a non-empty, closed, and invariant subset of lambda to z. What is invariant means that the whole set, if you shift it, you get the same set. So non-empty is often forgotten. This is a very crucial assumption. Very often in mathematical papers, you will see just a closed invariant set. And non-empty is in everybody's mind, but they forget to write it down. So be careful. Okay. So to make you more familiar with these objects, I prepared a few examples. The first example is trivial, as usually. And we take the whole space, lambda to power n, for example. It's one-sided shift. And if you shift the elements, you get, again, everything. So this is an invariant set. Now, another example is just one sequence. Sequence consisting of just zeros. If you shift it, you will get the same sequence. Another example is periodic. Periodic system is obtained by taking a block, finite word, so that means finitely many symbols, and repeating this block infinitely many times. But then this is just one point. We want the whole space, so you have to shift it again and again, again. Eventually, it will come back. Here is an example. If you shift this period is here 5, so there is only 5 elements. The 6th shift coincides with the first one, or with the 0th one. The 5th shift coincides with the 0th. Okay. Another example, very important, is subshift of finite type. Maybe you've heard this term already. It's very often used in dynamical conferences or papers. SFT. Everybody knows what SFT means. Subshift of finite type. It's very confusing, though, because this finiteness is hidden in the definition by negation. So I don't know how this can be compared to something from real life. I don't know. A finite man would be someone who visited everything except for finitely many cities. So that would be called finite cities man. Nonsense. And this is the same nonsense here. You take a list of forbidden words, and this list should be finite. And then you create all possible strings or sequences where these forbidden words do not appear. So it's by negation finite. Let me give you an example. A very famous golden mean shift, where you allow everything except 2 consecutive ones. So you can easily imagine how to create an element of this space. You can write anything you want, but after each one, you must put a 0. Then you may put as many zeros as you like, and then another 1, but after this one, you must put another 0. So here is an example of an element of this space. And if you shift such a sequence, it will satisfy the same condition. 1, 1 will not suddenly appear after shifting, of course. Okay. Another very famous example of a subshift starts with a sequence. It's called Morse sequence, or more precisely 2 Morse sequence, and it is built by the following rule. You write 0, and that's the only step which requires explicit naming the symbol. The first symbol is 0. From here on, you apply some inductive rule. Whatever you have written, you negate it and attach or concatenate with what was written so far. So once you have written 0, the negation of that is 1. So you add a 1. Then you have 2 symbols. 0, 1, the negation of 0, 1 is 1, 0. So you attach 1, 0. Then you stop again. You look what you've written. You have written 0, 1, 1, 0. The negation of that is 1, 0, 0, 1. And so on. whatever you've written, and the stops are always at powers of 2. The length is always power of 2, where you start your negation process. And then, of course, this is just one element, and there is a general rule in symbolic dynamics that once you have a single point, you can always shift it, shift it, shift it, shift it. You get countably many points. You take the closure in the space of sequences. The closure is in the topology of coordinate convergence. So you take any sequence that can be approximated by those shifts. And that's your system. And you can prove that it's closed by definition, that is invariant. And non-empty also by definition because it contains our 2 Morse sequence. Okay. So in symbolic systems, the notion of complexity simplifies. So it's funny because complexity simplifies. Simplification complexifies as well. Anyway, why? Because there is no epsilon involved. And the complexity at length n simply can be computed as the number of words of length n that appear in our system. Of course, if you change the metric of the space, because in this space there are many metrics compatible with a pointwise convergence topology. But with appropriately selected metric, this will be exactly the complexity with epsilon equal to 1, or anything smaller. So it stops being dependent on epsilon. Okay, now very important property of complexity. First of all, it's non-decreasing, that we already discussed. The number of words, of longer words, is always bigger than the number of shorter words. But it is also sub-multiplicative. If you take the sum of n, m, and n, you can imagine your interval of length m plus n, and you divide it into the first interval of length m, then of length n, and how many words can there be? Well, in the first part, you know how many words are there, CPL sub x of m. Then in the second part, CPL sub x of n. And jointly, of course, the maximal number of words that you can create is the product, because you can combine each word from here with each word from here. But perhaps not all of these words are allowable in your system. This is the maximum, so you have inequality. If you now take logarithm, then you have subadditivity. Logarithm turns products to sums. So we have this rule that logarithm of CPLX m plus n is less than or equal to the sum of logarithms. Now kicks in something very important, Fekette's lemma. If you have a subadditive positive sequence and you divide it by n, then you get something that converges. Moreover, it converges to its infimum. So it is not exactly decreasing, but it converges to the infimum, which is called maybe descending sequence, something like that. So we know that the limit exists. And this limit is very important. It's called the topological entropy. It corresponds to the notion of epsilon entropy for general systems that I explained earlier. But now it no longer depends on epsilon, so it becomes some universal parameter for the system. It does not depend on anything, just on the system. It does not depend on the metric, it does not depend on anything, just the topology. And it's denoted by h sub top of x. This is the key notion that I want to discuss today. Okay, so for example, if we take the full shift, how many blocks of length n are there? Of course, any combination of lambda. So we have hash lambda, the number of symbols, and we raise it to power n, because that's the number of blocks that exists in the whole world. But lambda is our, lambda to power z or to power n is our whole world in this case. So if you now take logarithm and divide by n, you get a constant. This does not depend on n, so it converges to log 2 of hash lambda. This parenthesis here is also in the wrong place. Should be here, not here. Anyway, okay. And because lambda to power z or to power n is the largest space in which we work, this is the largest entropy we can get. Okay. Next example is periodic. If we have a periodic sequence, then the number of blocks of length m, this is an easy exercise, is a minimum of m and n. So for the few steps, it's maybe m, but then it becomes, for the few steps, it may be n, but then it becomes constant m. If you take logarithm of a constant divided by n, it goes to 0. So periodic systems have entropy 0. Why? Because they are very primitive. They have only finitely many points. So there is no complexity involved. This is why. Okay, if you take the 2 Morse sequence or the 2 Morse system, then it is already much more complicated. The exact formula for the complexity is complex, but you can show that it grows linearly. It's below 4n. So now if you take logarithm of that and divide by n, you know that logarithm of n divided by n goes to 0. Logarithm grows much slower than linearly.
Sorry, may I have a quick question?
Yes?
I am. So, okay, as you explained, the exact formula for this complexity would be difficult, but showing that h top of x is 0 for 2 Morse sequence should be easier, yes?
You mean that the entropy is 0?
Is 0, yes.
Yes. Yes, there are simpler proofs than just.
So this bound is in some sense an overkill, yes?
In some sense, yes. I started by introducing entropy as a parameter associated with complexity, but you can do it by other means. But you need to know a little bit more about entropy for that. You can, well, I really don't know what the simplest proof would be, but the proofs that I have in mind right now, they use some information outside the scope of this talk. So maybe it's not the best way, I don't know.
Okay, thank you.
Now, subshifts of finite type are either periodic, then their entropy is 0, or they have positive entropy. So there are no non-periodic 0 entropy subshifts of finite type. And because I gave you this particular example of the golden mean shift, the entropy of that is the logarithm of the golden mean. That explains the name of the system as well. Well, it's an exercise to compute this entropy. I leave it to you if you want. This complexity can be calculated fairly accurately, or maybe it's easier to calculate the entropy directly by some entropy formulas, but we haven't covered them yet, and we won't. But what I wanted to focus on for today's meeting is this question. Pick any number bigger than 0. Can you create a subshift whose entropy is exactly that number? Is it possible? Well, what do you think? Yes, of course. And we can even give a proof. Very, almost complete proof. So, we will use the fact that the limit in the definition of entropy exists. And we will run over a subsequence. Instead of n, we will take 2 to the power k in a moment. So let us replace 2 to the power nh by its ceiling, the upper approximation by integer. And because we want the complexity to be an integer, it's the number of words. So this sequence is non-decreasing, clearly, but it's also submultiplicative. If you take the ceiling, without the ceiling, it's a multiplicative sequence, of course, because if you add exponents, you multiply. with the upper ceiling, it becomes submultiplicative. It's an easy exercise. So we have a subadditive sequence. Thus, logarithm of an is this was submultiplicative, so the logarithm is subadditive. By Fekette's theorem, it converges, and it is almost immediate to see that the limit is going to be h, because the rounding up becomes less and less important if you take bigger numbers. So the limit is the same as if we dropped the ceiling marks. Okay, so we have a base to construct our system so that the complexity follows these numbers, an. These are integers, so we can try to build a system for which the complexities are exactly the ans. But to be honest, I don't know how to do that. However, I know how to do that so that this equality holds for powers of 2. So this is why we will only go through the subsequence of n's. So we take n to be 2 to the power k. So we will build families f sub k of exactly a sub 2 to k elements. And we will call them admitted words. And their length will be 2 to k. So 2 to k now is our n. But it's not all n's, it's just selected n's. Okay, so for k equal to 0, 2 to k is 1. So we want to count how many words of length 1 we have. So this is exactly the cardinality of our alphabet. So what we do, we just choose our alphabet so that its cardinality is A1. A1 is some number. Once we have constructed families up to number k, which are words of length 2 to k, we will create, and then the number of words is exactly what we wanted. Here is the prescription how to make the following family. So look at this, 2 to k plus 1 is the same as 2 to k plus 2 to k, because it's times 2. So by submultiplicativity, this is less than 2, then a2 to k squared. Okay, so what is this a sub 2 to k squared? We know that a sub 2 to k is the number of admitted words of length 2 to k. And now imagine that we take one word and another word, and we concatenate them together. So the number of such concatenation is a sub 2 to k times, again, a sub 2 to k, which is a sub 2 to k squared. But maybe we don't need all of them. We want a sub 2 to k plus 1, which is less. So we just throw away and to the basket to trash some number of words so that the number of admitted words is exactly what we want. We can do that, of course. Except we want to keep all words of the previous family. So how to make sure that in this throwing away this trash, we will not destroy the family f sub k when constructing f sub k plus 1. This is just my idea I had while writing these slides. This is a very simple idea. Namely, we take so-called repeated words. So we take the word from the family f sub k and repeat it twice, like bb. How many such words there are? Well, the same number as we had before, so it's a sub 2 to k. We know that n increases, so a sub 2 to k plus 1 is bigger. So we can construct our family by first choosing these repeated words, and then some number of words that are not repeated, as many as we need for our a sub 2 to k plus 1. And we know that we can do that. So this means that we can arrange a family of the exact number of words. Okay, so here is an example. Let h be some crazy irrational number. I took pi over 4, just because we get nice example, not too large numbers. So an is the integer part, the ceiling of 2 to n pi over 4. And if you take a calculator and calculate the first few steps, we have a sub 1 is 2, then 3, 6, and 9. So how do we create our families? Well, the first number tells us how many letters we need in our alphabet. So we take lambda to be 0, 1, because we need 2 elements. Then we need 3 elements, okay, of length 2. But we want to start with the repeated words. So we take 0, 0, and 1, 1, and we need 1 more. So we take, for example, 0, 1. Okay, now we want to create F2. That will be words of length 4. We start with the repeated words. So we take 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1. But we need 6. So the next 3 are just any concatenations of 2 different elements from our family F1. So I took 0, 0, 1, 1, 0, 0, 0, 1, and 1, 1, 0, 0. The choice is absolutely free. And then the last one, we have 6 words. We take the first 6 are repeated words, and then the last 3, because we need 9, are any freely chosen concatenations from the family F2, and so on. Okay, so this is the way we construct longer and longer families. Now, how to define our space, our subshift. It's a little easier to define it for the invertible case, for lambda to power z. Namely, we define x as the set of sequences which are concatenations of the words from fk, and for each k this should be true. So here is a picture how the word should be constructed. So at the first level, the yellow level, you take a concatenation, you cut it like the yellow line is cut, and each of those pieces should belong to F1. But the first pairs, the pairs of the yellow ones, which are marked as green, they should belong to F2. And the red ones should belong to F3, and so on and so on. And you can show that this is non-empty and closed and invariant and so on. So this is how you create this system. If you want to do it for x to power n, it's a little bit more complicated, because what you do is you create the system for lambda to power z, and then you just cut all these words somewhere and take the right-hand side. And this sequence is not necessarily a concatenation at each level, because there might be some incomplete prefix. So in the definition, direct definition, you would have to say that your sequence is a concatenation from that family, plus perhaps a prefix which is a suffix of your allowed word from your family, something like that. So it's easier to say we construct it for lambda to z, and then we take the right-hand side halves. Okay, and the last step is complexity. We need to estimate the complexity. But we don't have to do it for each number. It's enough to do it for powers of 2. So for n equal to 2k, it is clear that we have already included the family fk as admitted words. They appear there. Perhaps some other words appear somewhere. If we shift a little our window, then you will see some new words, which is a concatenation of a suffix and a prefix. So there will be more words. But at least the family fk is there, so it's bigger than a sub 2 to k. And then if you calculate the limit, we know that the limit on the right-hand side is h. Maybe I should use this marker. We know that the limit is h, that was mentioned earlier, and this is at least that much. So we have shown one inequality. Fine. Now we need a lower estimate. And for the lower estimate, it's a little bit more complicated. We take some large integer m and take n equal to m times 2 to k, not just 2 to k, but m times 2 to k, which is so any word of this length is a concatenation of m minus 1 words from fk plus a prefix and suffix. So in this picture, these are complete words from the family fk. Here is a prefix and here is a suffix. The sum of the lengths is another to A sub, no, is 2 to K, right? So how many such words there exist? Of course, you can have all possibilities here. So it's a hash of fk to power m plus 2, because you can imagine that there is some complete word involved here and some complete word involved here. And the maximal number of words does not exceed this number, which is a sub 2 to k, because this is hash of fk, and to power m plus 2. And this plus 2 doesn't matter, because in the calculation of entropy, you take the logarithm of this number and divide it by our n. So by m 2 to power k. Now this m plus 2 comes out, and we get this fraction times the familiar term, which we know converges to h. All right, so we are getting this thing here. But m was arbitrarily large, so this fraction is as close to 1 as we wish, so in the limit, we have a lower estimate h. So finally, we have proved that the equality holds. Fine. That is half of my story and 3/4 of my time. But this is standard in some sense. Okay. So the dynamics was defined by a single transformation, but we were actually observing the iterates. And the iterates can be pictured as an image of either n or z. So also for calculating the entropy, we were actually using something that depends on the intervals. You see, this complexity of n was actually complexity of how many words you can have over the interval from 0 to n minus 1. And this n in the denominator was just the length of this interval. So you can rewrite this formula using the notion involving intervals from 0 to n minus 1. And what is a crucial property of such an interval? It's the following property. If you shift such an interval, here is a picture. You take a long interval from 0 to n, and you shift it a little bit. You shift it by some fixed k. But n is chosen later. It's much bigger than k. Then the proportion between the intersection, this is the intersection, and the whole length of my interval is close to 1. So this property is called Fellner. The set is almost invariant under a small shift. It loses a little bit on one side and on the other side, but it's not a big fraction of the whole set. And this property is actually behind the fact that we can prove the existence of the limit, and also that we can prove that this entropy is an invariant, and so on and so on. Okay. So another thing that was crucial in the construction was the partition of z into intervals of length 2 to k. Okay? And all these intervals for large k have the Fellner property. So we are trying to be more general now. We will consider more advanced dynamical systems where there is not just one transformation, but there is a whole semi-group or group of transformations. And actually we were already dealing with this because the powers of T were a semi-group of transformation if it was just a continuous transformation and we only looked at the forward powers. And in the invertible case, we were looking at forward and backward iterates, so we were looking at something that resembles the group Z. So we have an action of the group. And what is the action? It's a mapping that sends our group to the space of continuous transformation of our space. Or sometimes the C can be replaced by homeo, so it's a space of homeomorphisms. And this action should also obey so-called semi-group rule. That means if you take the product of two elements of the group, they should correspond to the composition. of the transformations. So the action group, the group acts, sorry, if it translates each element of the group to a continuous transformation or a homeomorphism, and the product corresponds to composition in the same order, because we don't want to limit ourselves to a billion semigroups or groups. Okay. For example, if we take two commuting homeomorphisms, for example, T and S, then we have an action of Z square, where what is an element of Z square? It's a pair, NM. NM corresponds to T to power N, S to power M. Because it's a billion, it doesn't matter how we order these two. You can check easily that the semigroup rule is satisfied. But as I said, the semigroup need not be commutative. Actually, we want to focus more on non-commutative because it's more interesting and more advanced. Okay, but if we want to speak about entropy, we need a notion of a Fellner set, because we want to copy the whole calculation. We also want to have a limit of some complexities and stuff. So we need the Fellner property. So here is the definition of a countable amenable group. First of all, we need a Fellner sequence, not just one set. We need a sequence of sets which have the Fellner property, which is better and better. That means if you take the set Fn from this sequence, and first of all, you fix some G. That was 3 in my example with Z. It was shifted, the interval was shifted by 3 units. So we fix a G. We take Fn and shifted Fn by this G. We look at the intersection. We look at how many elements the intersection has and compare it to the whole set. And we want this to be very close to 1 as n grows. This is the Fellner property with increasing precision, and we call this sequence Fellner sequence. This sequence allows us to calculate lots of objects that have been done for Z actions or N actions without even often realizing that the Fellner property is at work. Okay, so here is the picture of two sets. One of them has the Fellner property, the other one doesn't. The first set, if we shift it, the green area is the intersection of blue and yellow. We know it should be green. It's a large percentage of the blue. And in the second set, it's deliberately made so that it doesn't have this property. It's shifted by a very little, but it is almost disjoint with its unshifted copy. So it definitely doesn't have the Fellner property. So Fellner sets are in some sense connected, you may say so. So a semigroup or group is called amenable if it contains a Fellner sequence. And here are some examples together immediately with some actions. So the first very natural example is the semigroup of natural numbers, but with multiplication. It's a semigroup. And what is the most natural example of the action of this semigroup? Well, I don't know. I only know one example, to be honest. Namely, you take, by the way, what are the Fellner sets here? It's a little tricky. It takes a little work, but maybe you can prove it by yourself as an exercise. If you take divisors of factorials, this is going to be a Fellner sequence. You can imagine what happens with a set of divisors of a large factorial if you multiply all these elements by 3. Some will fall out, but not many. Many of them will already be there. Okay. So the action which I propose as the simplest example is the torus, the one-dimensional torus. So it's a complex unit circle. And you take the action by n as z to power n. So z goes to z to power n. So it is actually, how does it work? Well, you have a circle. Maybe I switch to drawing. How do I switch? Okay, you have a circle, And then if you take times 2, for example, n equal to 2, this interval becomes stretched twice. And the whole circle becomes also stretched, so actually it wraps around itself 2 times. This is the mapping. Z goes to Z square. And if you want Z goes to Z5, then you go 5 times. 4, 5. That's it. So you stretch, you straighten the circle, stretch it 5 times, and wrap it around the original radius. Okay, so let's go on. Now the semigroup rule, does it work? Yes, it does, because if you take the action of n times m, you have a product which corresponds to the composition. You take z to power m first, and then you take z to power m to power n, and the composition of products of powers results in product of the exponents. So the rule is satisfied. It's very tricky because this looks like an action of n. Many dynamists subconsciously think of this as the action of n with addition, but it doesn't work. It's the action of n with multiplication. Very, very curious. And to be honest with you, very little is known about this action. I know how to prove that it has entropy 0, for example. But we tried to prove with very good mathematicians. We tried to prove some more advanced properties of this system, and we failed because the Fellner sets are so crazy. If you look at the divisors of some factorial, that set is on the axis. It looks like some number of consecutive numbers, but then it starts jumping, and the jumps are crazy, and the distances between the 2 numbers are irregular. And of course, in general, it becomes less and less dense, but the distances are irregular. It has to do with the theory of prime numbers and so on. So it's very complicated. Okay, so let's take something easier. The group of, let's do something non-abelian, because n is abelian with multiplication. Let's G be the group of all permutations of n, but finite permutations. What does it mean? That means that you are allowed to permute only some initial digits. So in this case, 1, 2, 3, 4 becomes 4, 3, 2, 1. Uh-oh. Does it work? Yeah, there was a moment of silence, I think. And then the rest of the numbers stay at their positions. So in this group, notice that, first of all, it's non-abelian. A composition of 2 permutations depends on the order. Second observation is that every element has finite order. If you repeat the same permutation some number of times, eventually it must come back, because you are permuting actually a finite set. So this is very different from anything that we've discussed so far. N powers of n, and with multiplication, these are all groups with all elements of infinite order and abelian and so on. So what is the Fellner set? What are the Fellner sets in this group? Well, they are subgroups, special subgroups. Namely, if you fix the number of digits that are allowed to be permuted, that is a subgroup. And these subgroups form a Fellner sequence as your k-gross. So this definition of n is it's such permutations that for all k bigger than n, k stays in its place. Okay. So now I promise to give you examples of actions. So this group acts on one-sided sequences in a very natural way. Namely, if you have a sequence, you permute the initial elements according to the permutation. So for example, if we take this element pi, which is in the previous example here, we take this pi here, and we take an element, a sequence, a 0-1 sequence like this, then what happens? Well, very simple thing. We take the 3rd digit, which is this one, goes here. Then the 4th digit, this one, goes here. Then the 2nd digit, this one, goes here. And then the 1st digit, this 0 goes here. How can I delete it? Like this. Okay. So simply we permute the zeros and ones. Of course, many permutations may give you the same result, right? Because you only have zeros and ones. You don't know which zero went where. But it's an action and it's completely legal. The semi-group rule is easily checked to be satisfied. Okay. Another class of, my time is very little time left. Anyway, so another class of actions are symbolic actions. And the rule is the same. Instead of taking lambda to n or lambda to z, you take lambda to g. So the elements are functions. What is a function from g to lambda? It's simply on the group. At each element of the group, you put a 0 or a 1. Or if the alphabet is richer, you put the symbols. So you can imagine that this is a configuration of zeros and ones over the group. And this is the full shift space. We denote it as lambda to g. And the shift action is as follows. It's now very important because the group is not assumed commutative, that if you want to shift this element by some h, then you have to add this h. Something is not working. Okay, then you have to add this h on the right of your g. So your element tau sub h of x is such a y, which also has its coordinates yg, that yg is x sub gh. If you write hg, you won't get an action. The semi-group rule will be violated. Here is the verification of the semi-group. This is the abbreviated notation. H of x at g is x at gh. And the semi-group rule verification takes a little while because you have to be careful about the order of things. So if you want to calculate f of h of x at g, you first have to take f. The action of f produces gf. But we are still at h of x. So to calculate h of x at gf, you have to put gfh. And if you directly take fh at x at g, you multiply g by fh. And you check that these two are identical. So the semi-group works.
Sorry, just a quick remark. For groups, it works, but instead of h, you have h to minus 1, yes?
If you change the order, if you want an action,
yes.
If you want something like xhg, then you put h minus 1. And this is also a left action. Yeah, okay. So, problem which I am facing right now is, do I have any additional time or should I finish? As you see, I am on page 18 and there is 27. So there's still 9 pages to go. Up to the chairman. 5 minutes. Okay, I will try to say as much as I can, but okay, I will speed up a little bit. So the orbits are fairly obvious. You take the images of x by all the elements of the group, but you also remember the index. So it's not just the set, it's the function from g to the orbit. Okay, and then we have the same story, epsilon fn indistinguishability, but now n is replaced because n stood for the interval from 0 to n minus 1. And now we take just the Fellner set number n. The picture is the same, only it's much more complicated because various elements may go away and then come back. So this picture is more complicated. It doesn't follow a line like in z actions. Complexity is defined in exactly the same manner. You take a lim sup and you divide instead of n by the cardinality of your Fellner set. And symbolic systems are G subshifts, invariant sets, it's the same. And complexity in symbolic system, again, does not depend on epsilon. So The complexity at Fn is the number of patterns or blocks over the set Fn which appear in X or in the elements of X. Function, pattern or block is a just function from Fn to the lambda. And topological entropy is defined by the same formula as before, but now the existence of the limit is completely non-trivial. There is no Fekete lemma here. It's much more complicated. It takes Scherer's inequality to prove such things. But the limit exists still. Moreover, this parameter does not depend on your choice of the Fellner sequence, because in many groups, there are many Fellner sequences available. In Z, for example, you can take intervals from 0 to n minus 1, but you can also take intervals from n to 2n. And the next one is more to the right. They don't even cover each other. You can take a sequence of disjoint intervals, and that is also a Fellner sequence. This notion of entropy does not depend on the choice of Fellner sequence. And now we would like to mimic the construction of a subshift with a given entropy. I won't do that. I didn't even plan to do that. But what was essential, if you remember, was the partition of the orbit or of the symbolic element into intervals of length 2 to k in such a way that the longer interval was a union of the shorter intervals. So what we need to mimic this construction is the following special Fellner sequence. The Fellner sequence, we want such a Fellner sequence that it can be organized in so-called generations. So the first generation is from F1 to Fn1, then the following ones, and so on. So that each set of the k plus first generation is a union of disjoint elements of the kth generation. Here is the picture for that. So the colored figures are the first generation. And then they are organized in bigger sets, which are Fellner sets of the second generation. There is finitely many possible shapes here, but in this figure, there is always finitely many. And then these ones are organized in even bigger ones. So we have a sequence of so-called tilings of the group. And the most important theorem which I wanted to present today, and that will be all for today, is the following fact, whose proof is very advanced, and I'm just giving you the information that it exists. Each countable amenable group admits a Fellner sequence which satisfies these requirements which I just said. It can be partitioned into finite collections called generations, such that each of the set of the k plus first generation is a disjoint union of the sets from the kth generation. So this is a very important theorem which enables to do many, to prove many theorems that were known for Z actions and generalize them to countable amenable group actions. Okay, so here I had many nice pictures. For example, for Z square, you can take the first generation, like the colored figures here. Then you can organize these. You see, these are unions of the previous ones, but there are two shapes. Then unions of these two, but it doesn't have to be so complicated. You may take just little squares. 4 squares form a bigger square, 4 of the bigger, and so on. So this is a very crazy way of doing it, but I'm showing that there are many possibilities for Z2. This is the most natural one. You just take squares. Then for n times, it's more complicated. Here is the picture of n times. It's an infinite dimensional lattice because of the prime factors representation. And the Fellner sets are rectangles with increasing dimensions and increasing number of dimensions. So the first one is this little one here. Then if you take 4 of those, you get this flat thing. And then this flat thing can fill in this cubical thing. And so on. And you add more dimensions. This is not a 3-dimensional object. Fine. And then finally, the finite permutations. I will just show you the Kelly graph of this group, and here is the tiling. This is the tiling by F sub 2, permutations of 2 elements. You see they only differ by the first 2. Here is 1, 2, 3, 4, here is 2, 1, 3, 4. So the 2 are just permuted. And these are copies of this set. Then if you take 3 elements permuted, you get this picture, and then if you take 4, this picture, and then 5 and 6 does not take. But in all these examples, the group could be tiled with just one shape in each generation. And this is an open problem, which I recommend for you to study. And this problem was posed by Benji Wise. Is every countable amenable group monotilable? That means, can you create a tiling such that in each generation there is only one shape? This is unknown. All examples that we know can be partitioned with one shape, but in general, the general proof requires many shapes. We don't know how to do it. Thank you very much.
Thank you. Thank you very much. Questions?
What do you expect from this problem? That the answer will turn out to be positive or negative?
Well, it's an open problem. I don't expect anything.
No. What I have in mind usually for the word of the whole word of all possible groups, every conjecture which is formulated for all discrete group finally turns out to be false. This is the slogan of Gromov.
So I can just tell you that the proof that we have does not really involve the algebra of the group. It involves the Fellner sets, of course, the Fellner property, the amenability, but the algebraic structure of the group is not involved in the proof. So maybe some algebraized, maybe if we have a classification of all countable groups and we know how to deal with them. There are groups with finitely many generators, there are groups with infinitely many generators. There are thousands of algebraic properties which classify the groups. And in many of these classes of groups, I imagine the proof for monotiling property can be done. But can we actually grasp the whole variety of countable groups so that an algebraic proof could be possible? That I don't know. I am not an algebraist, so I don't want to make false guesses. But the question is, of course, very interesting.
Okay, thank you.
Okay, I have a question about this the notion of amenability, because for groups I knew before the notion which says that the group is amenable if there exists a probabilistic measure on all subsets, which is invariant on their multiplication.
Yes, it's finitely additive.
Finitely additive.
Yes.
And does it agree? This definition from your lecture, it agrees?
Yes, it's the same. It's the same property. There are many proofs that these properties are equivalent, and there are other equivalent definitions as well, and properties which are only true in amenable groups. Yes, that's
okay. Thank you.
Hello. I think I have two little questions, but I need to ask the first one first because I don't know if the second one will make sense. So you mentioned the like the exponential and sub-exponential dynamical systems, right? And
sub-exponential complexity. Yes.
Yeah, in complexity, yes.
They all have entropy 0. If it's sub-exponential,
entropy 0.
But the world of entropy 0 system is as rich as the world of all systems.
Okay, perfect. Yeah, I think then my second question will have a negative answer. I wanted to ask if the like amenable groups have any? I think there was some sort of characterization of non-amenable groups having like exponential growth in the Cayley graph, something like that. I once said something.
Yeah. So
I wanted to ask if the
any
notion
group that is sub-exponential is amenable.
Okay, yeah.
So for a group to be non-amenable, you need exponential growth at least.
Okay, but
cannot
these
have more.
notions of growth and complexity are completely separate then. Do they have some relation?
They do, yes.
Oh, really?
They do. The usual growth is calculated for the sets so-called SN. You take the number of generators. It's calculated more easily for groups with finite number of generators. So call this set of generators S, and you look at S to power N. And you look at the complexity as just the cardinality of S to power N. And for example, in free group, it's cardinality of S to power N. It grows, there is no connections. Yeah. But for abelian groups, it's going to be, for example, in Z2, it will be Z square, right? N square, because you have squares, right? You generate squares of size N by N.
So it's like you're studying like the dynamical system of the action of the group on itself?
Yes, you can, of course. You can accept that we are more interested in actions on compact spaces. So it's usually not the group itself, it's some compactification of the group on which the group acts, and we have a dynamical system which is compact.
Okay.
Not always metrizable. If you take some beta compactification, then of course you are out of metrizability. Outside of metrizability, so it's
okay. But then I'm sorry, I got a bit confused with this. So it's not that the entropy itself has something to do, like the exponentiality of the, I mean, the complexity of the system has something to do with the group.
With the complexity of the group.
Yeah.
Yes, I think the answer is positive. There are groups that can only have zero entropy dynamical systems, actions oh no, that is nonsense what I'm saying, sorry. There is always no, that is nonsense, sorry. On each group, if you take the full shift, it will have entropy logarithm of the alphabet. So, no, that was nonsense, sorry. The complexity of the group, I don't think that you can connect it with the complexity of the dynamical system.
Okay, yeah, I thought it could not have much to do, but I still wanted to ask. Thank you.
Mm-hmm. You're welcome.
Questions?
Okay, I have two more questions. Since you mentioned this beta compactification, so the notion of entropy still does make sense?
Yes, you can define entropy for non-metrizable systems as well. Yes, but of course that will be infinite. If you take the action of the group on beta compactification, it will have infinite entropy.
Infinite.
Yeah.
Okay.
Yeah. Entropy can be infinite on a general compact space.
Not
if we are talking about symbolic systems with finite alphabet, it's always bounded by the logarithm of the cardinality of the alphabet. Symbolic systems have bounded entropy. But if you take the action on a connected space or on the beta compactification, for example, or even it's enough to admit countable alphabet, like 1-point compactification of natural numbers with infinity, and use this as your alphabet for the symbolic system. Oops. It sometimes goes deaf. So then it is infinite. The entropy of such a subshift is going to be infinite.
Okay, so it is possible to have infinite entropy still in this context of metrizable spaces?
Of course, yes.
Okay, and my second question is about something which has intermediate growth. faster than polynomial complexity, but smaller than exponential. How hard is to construct such an example?
You need to know a little bit about symbolic systems and the way of constructing them, but it's not very hard.
Okay, not very hard. And
For example, an easy example, I can give you one, which I just freshly remember. We call it a stuttering subshift. Stuttering is to like, I want to say. So you take a block. You have two interlaced types of steps. In even steps, you repeat the same word. You have some list of words so far, and then each word is repeated 3 times. And that's your new list. And then in the next step, you take arbitrary concatenations from the previous family. So maybe I can draw something here. So I don't know if I'm drawing or marking. So your first word is, for example, what happens here? No, this is happening exactly what should not be happening. Ah, the lowest one, and then, okay. So you have a list of words. So for example, I don't know, B, C, D, that's enough. And then this is your first family, E, okay. This is your first family, F1. And then you take B, B, B 3 times, and C, C, C 3 times, D, D, D 3 times, E, E, E 3 times. This is your second family. And then your third family is arbitrary concatenations from the second family. So you take, for example, B, 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 C, 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 D, 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 and you put some limit, maybe 5 times. So maybe B, B, B again, and B, B, B again. Okay, 5 times. And you take all such things. So you have a large family. And then your next step is you take these words and stutter. So you repeat them maybe 20 times. So you have the same cardinality because each word produces just one, but they are repetitions 20 times. And then you concatenate. And by choosing these parameters, how many times you repeat and how long free concatenations you choose, you can actually create any intermediate complexity. Yes, it's going to be sub-exponential, but if you take any sub-exponential sequence, you can make this complexity higher than your a priori chosen sub-exponential sequence. So it will be still exponential, but it's squeezed in between your given sequence and the exponential growth. So by playing with these parameters, you can do that.
So last follow-up question. Is it also possible to perform analogous construction in the case of groups and in the growth of the group?
Yes,
on a
yes. Once you know the tiling technology, especially for monotiling groups, for monotilable groups, you can repeat the same construction very easily. Because you know that you have a big tile, which is concatenated from smaller tiles, and these, again, concatenated smaller tiles into bigger tiles. So you have odd steps and even steps. And in odd steps, you repeat the same word 4 times, and then you concatenate freely all such objects 4 times. And in the next step, again. And the number of times 4 is just an example. You can make it 16 times if you want. So again, you can play with this in the same manner. And if the group is not monotilable, it's more complicated because the cardinalities are not equal, so you have to play more carefully, but it's possible. Yes.
Okay, thank you.
Yeah. Any other questions? Maybe I ask a question. You discussed the systems of finite type for in 1 dimension. Yes.
Yes.
What about systems of finite type on Z2, for
on
example?
Z2, oh, that's a tough question, really, because there are many possible definitions. And actually, in Z2, it's still not so bad, but in Z3, there is a jump. And if you forbid some words, because the rule is to forbid words, but there are also other rules. You have graphs between symbols, you draw arrows, and you allow this letter to be followed by this letter, but not by another because there is no arrow. Or for longer blocks, you can draw such graphs, and every such graph produces a subshift of finite type. And on groups, of course, your graph will have to somehow respect the structure of your Kelly graph in the group. And it's much more complicated. And there are very strange phenomena. For example, you may have a subshift of finite type where the rule admits all size, every size, or maybe some size of words, but the whole space is empty. There are no words, infinite words, where everywhere you have the rule. So there are crazy things happening. So this is a tough question for subshifts of finite type even on Z3, I think. On Z2, it's a little easier, but on Z3, it's terrible.
There's a work to do.
There has been done some work on that as well, yes.
Any questions? Maybe just a question from Zoom.
Okay.
Zoom people, do you have any questions? I don't think.
So where is?
No. They should talk. Yes, so they can.
Why doesn't it?
It's okay. It's okay.
O, tu mamy ancymomów, ale wszyscy powyłączali mikrofony.
Okay. So if there are no other questions, then thank you again, the speaker, for the introduction to the chemical systems.
Thank you for your interest and interesting questions. It was a pleasure to present this lecture. Thank you. Nie chcę czegoś nacisnąć bez sensu, bo tu